Hello. Thank you guys for coming out to my talk. I'm going to try to keep this pretty informal and fast and try to keep the explanations, I don't know, just like I'll try to keep it going quickly and then I'll leave some time at the end for questions. So I'm going to be talking today about the bottlenecks that exist in Ethereum right now and some ways to try to address some of the different areas. And again, my name is Keone Hon. I'm the co-founder CEO at Nexus Labs. All right, so first of all, just to state kind of the obvious, there's at least 4 major resources that we're trying to conserve and trying to price appropriately within a blockchain. Those are the network bandwidth, the CPU throughput, the state access throughput, i.e. the SSD access throughput, and lastly, state growth. And just to state the obvious also, there are ways to cheat to try to address some of these bottlenecks. So for example, for networking bandwidth, you could just raise the minimum requirements for networking bandwidth on a validator. Or you could also require the nodes to all be physically very close to each other. And sometimes we see that in different networks, although it's not often really publicized, but if you like do a little bit of pinging, you'll get a sense of the fact that all the nodes might actually, or 85% of the stake weight for a particular network might all be in one geographical region, which is kind of crazy. So that's one way to kind of address one of these bottlenecks. CPU throughput I won't really talk about because I think it's not really generally constrained. That's another misconception I feel, is that people think that parallel execution is about being able to do a lot more compute at the same time, but actually the raw CPU time is not generally the bottleneck. So anyway, just to say, like, you could address this with bigger computers with more cores, but this isn't really a constraint. State access actually is the biggest constraint because the cost to read something from SSD is on the order of 100 microseconds, as opposed to about 1 microsecond or less for reading from RAM. So there's a huge incentive to just keep all the state in RAM and raise the RAM requirements. And then state growth, let's just ignore that for a second. So the point is, like, when designing a decentralized system, one could cheat on some of these different areas, but then that has a significant impact on decentralization. So what we'd like to do really is get the most out of commodity hardware, preserve decentralization by maintaining reasonable RAM requirements, reasonable bandwidth requirements, and full geographic decentralization across the stake weight. And in order to do that, we need to come up with better software architecture and really optimize the low level. All right, so there's sort of 4 major improvements. I'll actually, and it's funny that the numbering is like this, I'm so sorry, but it's actually coincidental because I'll be talking about the second number 1 and the number 2 and number 3 today. I think mono-BOT is really interesting as well, but just in the interest of time, we should just focus on the other ones. So asynchronous execution, parallel execution, and a new database called MongoDB for parallel state access. And when we stack these different improvements on top of each other, the cool thing is that there's actually a multiplier effect from one improvement stacking on top of another one. And that's how ultimately we can unlock much more throughput for Ethereum or an Ethereum-like blockchain. All right, so first talking about asynchronous execution. I want you guys to, I don't know how many of you are movie fans, but there's a movie that I really like called Limitless, and the idea is that the premise is that you only use 10% of your brain. So if there were like a drug you could use that could make you use 100% of your brain, you'd be so smart, you would be literally unstoppable. And of course in the movie, someone takes this drug, and at first it's awesome, and then there are a lot of problems that ensue from it. But in asynchronous execution, we can effectively give blockchains the limitless drug, making much better use of their brains, so to speak, without actually any downsides. We'll get to that. So for background, most blockchains have interleaved execution between execution and consensus. And so the thing that is kind of easy to understand is that consensus is expensive because it involves round-the-globe communication, literal multiple rounds of communication all the way around the globe. That's going to be expensive. And so in most systems, execution is a prerequisite to consensus, and in fact, there's multiple rounds of execution, communication. So it means that the execution budget is actually very squeezed. It's a very small fraction of the total block time. And so, the execution budget is actually a small fraction. So for example, in Ethereum, 12-second block times, the rough budget for execution is about 100 milliseconds, which is crazy because it's only 1% of the total block time. And so you have this, like only use 10% of your brain kind of scenario going on here, where we only actually get 1% of the block time to execute. And so what if we could make a change somehow so that we could use the whole block time? So now look at this schematic. So I've drawn execution as the dark square and consensus is the light square, and an interleaved execution, just very schematically, there's like interleaving between these two. And so if we kind of make another graph with time on the x-axis and blocks on the y-axis, we get something like this. And so the really simple explanation for asynchronous execution is that we're going to have nodes come to consensus without executing at all, and then we'll have execution just lagging a little bit behind. And so the way that it looks is like this. There's consensus on block number 1, and then as soon as that completes, then two things happen in two separate swim lanes. We do consensus on block 2 and also execution on block number 1, which we just consensused over. And so now the diagram looks like this. And so then repeating that schematic that I had before, it looks, not too different right now, but execution is now happening a little bit after consensus. And so just to state it very clearly, the pattern here is nodes are talking to each other and agreeing on the official ordering of transactions, but they haven't yet executed those transactions. So they're just agreeing on what the official ordering is going to be. And this subtle change to move execution out of the hot path is actually really significant. Why is that? So here I'm showing the two different schematics that we had from before, where now execution is just like a little bit after. And it doesn't look that different right now. But then what we realize actually is that we can increase the size of the dark rectangles substantially and actually just raise the budget, literally just raise the budget for execution, because we can now use the full block time to execute as opposed to only a small fraction of it. So that's all it is. Like asynchronous execution is a fancy name, but the concept is really simple. And it means like moving the execution out of the hot path means more time for execution. So we could just literally do more work in the block time. So just to point out a couple of quick things, every node is now is doing the execution independently. And so one might worry that although all the nodes have agreed upon the work to be done, and therefore they should always maintain the same state, because if they're starting from the same starting point and they're doing the same work, they should then get to the same state. You might worry that like one of the nodes gets hit by cosmic rays or something, has a bit flip error somewhere. So we still need to have some special checks in place to allow individual nodes to make sure that they haven't made an error somewhere and fallen out of sync. That's a little bit out of the scope of this discussion right now, but we can talk about it if you have questions. And then the other thing to point out is that now nodes are coming to consensus with a slightly delayed view of state, which could, one might worry this could open the nodes up to attacks where someone spams from an empty EOA. And so there's some ways to address this problem as well, which we refer to as the gas balance problem. Again, a little bit out of the scope of right now, but we can talk about it later if there's interest. Finality, lastly, one thing to point out, finality is a consensus time. So as soon as the block is finalized, that means the ordering is determined. That means the state is actually completely deterministic. So even though execution is lagging by a little bit, finality happens at consensus time. Okay, so I'll just move on really quickly. Second concept, optimistic parallel execution. I think intuitively everyone kind of understands what this, the idea of parallel execution just means literally doing more work in parallel. But what's really interesting to talk about is how we can marshal that work and ensure that we always get the same end state as if we executed serially. So in Ethereum, transactions are linearly ordered and serially executed. And in Monad, or in optimistic parallel execution, we still want the transaction to be linearly ordered, but then we just want to more intelligently under the hood do work in parallel and get to the same end state as if we just executed serially. All right, so this, and apologies, it's a little bit wordy. but I'll just say the algorithm one time as clearly as I can so that everyone has a sense of what it is, and then we'll go through an example. So the idea of optimistic parallel execution is super simple. It is literally just run a bunch of transactions in parallel, assuming that they're starting from the same starting point. Like assuming that the state of the world is the same for all of them. That's what optimistic means. And then generate a bunch of pending results for each of those transactions we ran in parallel, where a pending result means we do bookkeeping to keep track of the storage slots that were read in or that were mutated. And basically, like, generate a bunch of pending results. Each one has a list of inputs and outputs. And then in phase 2, we step through and commit those pending results in the serial order. So we commit them in the original order that the transactions were defined in. And as we're committing, then each time we commit, we check the inputs and make sure that they haven't mutated. If an input has mutated, then we go re-execute that transaction. Okay, so that was kind of a mouthful. Hopefully it was still okay. But I think the better thing to do is actually just to give an example. So I want you to imagine that the state of the world at the start of some block is like, I have 1,000 USDC in my account, Alice has 0, and Bob has 300. Okay, I have 1,000, Alice has 0, Bob has 300. And then just imagine that there's like 4 transactions, the first 4 transactions in the block. The transaction number 1 is me sending Alice 100 USDC. Transaction 2 is something unrelated, and then transaction 3 is me sending Bob 100 USDC. And then transaction 4 is something else unrelated. So again, I'm sending Alice, and then I'm sending Bob 100 USDC each, and I started with 1,000. So intuitively, we all know that what should happen is like I end up with 800, Alice has 100, Bob has 400. So now let's see what happens in optimistic execution. So the thing to point out about optimistic execution is that it's assuming that everything is starting from the same state of the world. So optimistic execution actually makes an error here, which you can see right up front, is that transaction 1 starts with an input of me at 1,000, Alice at 0. That's actually fine. But then transaction 3 starts assuming that I have 1,000 USDC in my account and Bob has 300. And that input is actually wrong because, as we all know, by the time that transaction 1 executes, it's going to mutate my USDC balance from 1,000 to 900. So let's just kind of step through this and see that. So, you know, we generate input, we run these transactions in parallel, we generate inputs and outputs, and then you could see here that transaction 3 is doing the wrong thing because it assumed I started at 1,000 and ended at 900, but actually what we know it should be is it should have started at 900 and ended at 800. Okay, so then we just step through these transactions one by one. So transaction 1 is committable because there's no, like the inputs are still correct. Transaction 2 is unrelated, so it's committable. And then transaction 3 has a problem because, again, and I said it already, but the input was assumed to be 1,000, but the current state of the world is 900, so this is bad. So then we just go re-execute, now redo it, and now we get the right result. Okay, so literally, and I realize that this seems really simple, and the reality is that it is actually a very simple algorithm. There's no like crazy magic here. It's literally an intuitive algorithm that does bookkeeping and, you know, it has this property that makes sure that we get the same end result as if we'd executed serially. So just to point out, no transaction is executed more than twice in this algorithm. And the other thing to point out is that, the rescheduling. So in the event where we do have to go reschedule work, you might be worried that this is going to be expensive because, you know, now we're going to have to go back to the disk and reread the value. But the good news is that almost all the time rescheduling invokes the same storage slot that's already been cached, so that re-execution is actually generally quite cheap. And so as a result, now we have an algorithm that can do a bunch of work in parallel, and more importantly, can trigger state access patterns in parallel. So it can start invoking a bunch of reads to the disk in parallel, which then can utilize an underlying backend that can read from the disk in parallel. Simple, compatible, and no access lists. All right, so lastly, and I'll be really fast with this one. So efficient state access. I said at the beginning that the biggest bottleneck is actually the state access. And so to kind of go backward a little bit, I want to mention that SSDs are actually extremely powerful, and they get better and better every single year. You should think of an SSD as a system, like a bottle that has a very wide bottleneck. That means you can actually read a lot of data from the SSD as long as you have software that can utilize that bottleneck efficiently. And the problem in existing Ethereum clients is that the access patterns for reading from the SSD are really quite terrible because, you know, it's like we run one transaction and that invokes some S loads or some S stores that causes a hit to the disk, and then, you know, that transaction has to complete before we start the next one and start reading the next set of things that are dependencies. So fundamentally, optimistic parallel execution means that we're getting slightly better access patterns, but then in addition, the number of reads that are needed is going to be, in existing clients, quite inefficient because of something I'll talk about in a second. So more quick facts, SSDs have quite high bandwidth, but they have high latency. So it costs 100 micros to read one piece of data, but then on the other hand, they can do about, you know, a good SSD can do 1 million I/O operations per second. So it's really important to saturate to get all those million IOPS out there. And Ethereum lives in the Merkle-Patricia tree. So this is a data structure, as we all know, that has a property that it's a commitment to the entire state, there's a successive hashing such that the root of that tree is a commitment to all the state in that tree. And if for various reasons, it's quite important that the Ethereum state lives in this Merkle tree. It makes bridging a lot easier. It means that when you and I are both running our nodes and we want to compare and make sure we have all the same state, we could just check the Merkle roots. It's super convenient for composability, but the problem is that maintaining this Merkle tree is quite inefficient. And to top it off, the existing clients basically embed this database, this Merkle tree structure, inside of another database, which under the hood has another tree structure underneath it. So the problem is that when navigating down to any root in the Merkle tree, each of those nodes that we visit under the hood is actually causing a traversal in another tree. And so there's almost like a quadratic amount of reads that need to be done just to navigate to one node in the Merkle tree. So the thing that we should obviously do is actually just store the Merkle tree natively on disk and sort of have a mapping between the tree structure and the actual pages on the disk. And that means that we're going to have far fewer lookups, so we can do far more parallel lookups. So that's what MonadDB is. It's a custom state database storing Merkle tree natively on disk. It's using asynchronous I/O. It has support for asynchronous I/O, so better support for effectively parallel reads. And then it has a lot of other optimizations, like bypassing the file system. And so at the end of the day, this means we have parallel access to all this Merkle tree state, which then, you know, if you stack that on top of parallel execution, and then you stack that on top of asynchronous execution, ultimately has a significant improvement to the overall throughput of an Ethereum-like system. Lastly, I just want to mention that although all this work is closed source at the moment, that's just because our team is under active development building this out. We'll be open sourcing prior to Monad mainnet, and also look forward to collaborating with the broader Ethereum research community and looking to push improvements back to Ethereum as well. And I'll pause here for questions. Thank you.
Hey, great talk. I had a question on, so if you're performing consensus on the transactions prior to execution, and you're performing optimistic concurrency control, how do you prevent user-level DOSes for pushing you down the worst-case path of your optimistic concurrency control logic?
Right. So I think your question is, I'll focus on the OCC part of it, aka the optimistic parallel execution part of it. I think the asynchronous execution is an interesting element because there's a little bit of shielding potentially for the leader might not know what that list of transactions is. But yeah, more generally, our team is spending a lot of time analyzing worst case scenarios. Like basically what is the adversarial situation where you have to you have to re-execute a lot of transactions because of invalidation of inputs from the previous transaction. I will say that for most cases that we've seen, the dependencies continue to be in cache, like in RAM, and so that lookup is fast. But yeah, at the end of the day, there is a limit to like, yeah, I think at the end of the day, it's possible that we'll explore like changes to fees in order to like penalize this kind of issue. But yeah, there's just a lot of research going into this right now. Thanks.
Thanks.
It seems like timing games and MEV are a big part of what Ethereum's struggling with. So how does that come into delaying execution?
Yeah, that's a great question. The planned default block packing algorithm is a priority gas auction, perhaps with some changes to how gas is charged, specifically charging a function of not only gas usage, but also the gas limit, so as to properly reserve the block space. Like if someone asks for a lot of block space, like they set a high gas limit, but they end up not using very much because they revert immediately, charging some function for that. But yeah, I think the MEV space on Monad is generally quite unexplored, and it's exciting to think about what's possible in an environment where there's much higher throughput, much higher gas limits, and much more frequent block times, and what the mechanism for submitting transaction ordering preferences is.